Okay, so next we are going to look at joint E. Kind of going in the clockwise manner there. We could do D first if we want. If you watch the D video before the E video, you'll see that we already solved for DE, but we'll solve for DE here if we need to. Oh, since we need to. So we're going to look at joint E. So we're going to do the free body diagram again. Only the segments that interact with that joint E are going to be included in this diagram. So we have the force of 500 in the Y direction that was given to us already, and then we have the force of member EC or CE, which we calculated from a previous video as 1096 of compression. So it's still applying compression to joint E, so it's going up and to the left. Every angular vector is made up of two composite vectors in the X and Y direction, and we solved for those already, so let's not do the work again. We've calculated that those two legs still are 775 and 775. If you missed how we did that, we just solved that right triangle. We have 45-degree angle. You've got the hypotenuse. You can go ahead and do the inverse sine, or the sine of X is sine of 45 equals X over 1096, whatever you've got to do. So we had those calculated. Let's not do it again. We're going to go ahead now and put the force of member DE. Force of member DE is in the X direction, so that's one of our unknowns that we haven't solved for yet. And then the other unknown that we have is the force of member BE. So the force of member BE, let's make sure we get the right colors. We keep everything color coordinated here. Force of BE, we're going to assume tension, so pulling away from that joint E itself. It is an angular vector, so it has two composite vectors. It's going to have a force of BE in the X direction, and it's going to have a force of BE in the Y direction. So this is the free body diagram. All of the different lines that are touching E, then all the composite vectors of the two angular vectors of the force of BE and the force of CE that are there. So once we get that picture and we put our knowns and our unknowns, the force, sum of all the force in the Y directions equal 0. So let's count. We've got 1, we've got 2, and we've got 3 different forces in the Y direction. The 500 is going down. The 775 is going up because it's applying compression that we calculated earlier. That's why we noted that compression. So we've got 775 going up in compression has to equal to that 500 going down plus what other force going down, because we need that equilibrium. We need everything equal, so that force of EB in the Y direction is that unknown force in the Y direction to make both sides equal, so it's 275. So we plug in that 275 for that force of EB in the Y direction. So now we're solving that green right triangle. That green right triangle has an angle, we now have a side, and we have a hypotenuse. So we've got to calculate what that angle is. So we've got to calculate what that angle is by looking at the distance from here to here is 2. It's on top of your sheet. I didn't pull this down far enough. And then this is 3. So you have 2, 3. That's there. So the inverse tan of 3 over 2 gives us 56.31. So the 3 right there. We'll draw it into here just for a visual instead of just talking about it. The tan of that unknown angle is opposite 3, adjacent 2. Punch it into your calculator. You have got that. So now we have two equations. We have the sine of 56.31 equals the force. So we're going back to this green triangle. We've got the force of EBY, which we knew was 275, over the hypotenuse, the force of BE. And then we can solve for the adjacent by using the tangent. So the tangent of that 56.31 is equal to the opposite, 275, over the force of BE in the X direction. So punch that in the calculator with the first one. We had 275 divided by the sine of 56.31. We have the force of member BE is equal to 331. Then we got to solve for the force of BEX. Just kind of keep things constant, just in case we need to use it somewhere else when we're trying to solve something. We go through and we take that 275 divided by that tangent of 56.31, and we end up with 183. So now we have the red triangle is complete from a previous problem. We have the green triangle that's complete. Now we've got to go look at sum of all the force in the X equals 0. So we have three forces. We have now one force in tension, one force in compression. So the 775 is in compression. We have the 183 in tension, but both of them are actually working in that same direction because they're both pulling and pushing that joint to the left. So that 183 is tension down and to the left, and the 775 is up and to the left. So therefore, that force of member DE needs to be going right to help that joint in equilibrium so it doesn't move for us. So we take 183 plus the 775, and we end up with the force of member DE in that X direction being 958. So we're going to go ahead and fill that into our chart with our knowns. We had the 958 compression. We had the 331 in tension. Now the only thing we're missing is that force of that member DB. We can go to joint D and solve that, and then we can call this a truss that has been completed.